Hi, welcome to this video. Remember, in this video, I will be doing a continuation of where we left. Remember, we are now discussing the reactions of the alkenes. We have spoke about 4 reactions of alkenes. So in this video, most definitely I'll be doing a continuation, but I will starting with the epoxidation, which is one of the reactions that alkenes actually undergoes. So now let us have a look at an epoxidation reaction and how does an epoxidation reaction takes place. Now, during epoxidation reaction, we're going to take an alkene, and on that alkene, we are going to add an oxygen on an alkene molecule. And therefore, we are not only going to add an oxygen just so. The molecule that's going to help us to add an oxygen during this type of reaction, it is what we call a peroxy acid. A peroxy acid, it is a molecule that has oxygen in it. So that oxygen will now be added onto an alkene to form the compounds that we call the epoxides. Okay, hence why this reaction it is called epoxidation reaction. So number 5, we are going to discuss only 2 reactions under epoxidation reactions. So the first reaction that we are going to talk about, it's reaction number A, and we are also going to talk about the reaction number B. So the difference between these 2 reactions is that it is true, we are adding peroxy acid onto alkene on reaction number A. Same applies on reaction number B. This is an alkene. We are still adding the peroxy acid. So what is the name of peroxy acid that we are going to add into our alkene? It is called the meta-fluoroperoxy benzoic acid. So this is a benzene group. We can see that the benzene group with halogen, and then we have carboxylic acid functional group over here, hence why this is an peroxy acid, okay, which is attached to benzene ring. So when we add again, the very same peroxy acid, it is abbreviated in this way, MCPBA. So most of the times when they say to you an alkene is reacting with MCBA, just know this is a peroxy acid. You don't have to remember all of these for sure. We are not being assessed on how to draw this and so forth. But for safety, just know how this MCPBA actually looks like, okay? And maybe know how to draw it. So reaction number A and B, those are the similarities. We're adding alkene to MCPBA. Now, let's have a look at the products that are going to be formed out of these 2 reactions. And the product that you're going to form here, it is a cycloether. Okay, there is a group that we're going to study as time goes by, which is called the ethers. So here we have a cycloether, which is a cyclic molecule, and then here we just have open ether, which is just an ether as it is. So the difference about these 2 reactions, here it's cycle, it's a ring, and then here it is not a ring structure. And then these are the products that are going to be formed during this chemical reaction. So now let's have a look at the very same reactions. How does this product manage to be formed? Like I said, we're going to add an oxygen into double bond. Remember, double bond, it has carbon-carbon. So that means when you add the oxygen, you're going to break that double bond, and therefore the oxygen will be between these 2 carbon atoms. And you can see that this is how we draw the addition of oxygen. And these hydrogen atoms, they have always been there on the sides on our carbon atom molecules, just that we broke that double bond by adding an oxygen. I hope that was clear. So again, the here for this reaction to take place, we're going to have to take our peroxy acid and then dissolve it in CH2Cl2. Remember, we have discussed this formation of dihalide. We say this dihalide, it acts as a solvent for other chemical reaction to take place. So that means peroxy acid will have to dissolve in this solvent so that peroxy acid can react with an alkene. So we form a cyclic ether. So reaction number B, same applies. We're going to take our peroxy acid. For sure, it has to dissolve, and our peroxy acid will interact with our alkene. But but this is an open chain, it's an open ring, so that open chain, so that means it is not a cyclic molecule. So what is going to happen is we're going to have to break this double bond between these two consecutive carbon atoms by adding an oxygen, and therefore our molecule will result in this way, whereby our oxygen, it will be written in this way. I hope that was clear. And therefore, now this is what is happening. Under reaction number B, we have further reactions. I'm calling it B1 and B2. So these, it's when we are doing the synthesis. Remember, like I said, from the synthesis, you'll be talking about compound A forming compound B, compound B forming compound C, compound C forming compound D, and so forth. Maybe our final compound that we want to form during this chain reaction, it will be compound number E. So that means these are the syntheses that we need to learn. These are the combination of these reactions that we have just learned about. We can see that if we want to form a diol molecule like this is called the diol molecule because it has two hydroxyl group substituted in it. So maybe we start with an alkene. We have to understand that alkene, there is a reaction that jumps from here to here, but I'll show you shortly. So now, say for example, we want to jump from alkene to an ether, and then from an ether, we'll jump to a diol molecule. So this is what you're going to do. Remember, we have discussed number B. We know how does this ether managed to be formed. And therefore, from this ether, we are taking that ether, and then we are reacting it under acidic conditions. So under acidic conditions, what type of reaction are we actually talking about here? We're going to talk about the reduction reaction, because you're going to have to add the oxygen molecules, the hydrogen atoms or protons into this molecule. We're going to protonate our ether. When you protonate your ether, you will form a diol molecule. So now how is that going to take place? Remember, we have H3O plus. We are not interested on mechanism, but I'll just quickly explain this. So H3O plus, oxygen, hydrogen will protonate this oxygen, and therefore you're going to have an OH like this. And therefore, the radical that is open over there, we're going to have a remaining H2O. The H2O will come here, and therefore another molecule of H2O will do what? Will steal hydrogen from that H2O over here, and then we're going to left with OH over here, which is what we see over there. So in this case, you have to understand that the product that forms here can further undergo the reaction to form a diol. But remember, where did we start? We started with an alkene because we're still under the alkenes. Okay, so this reaction that we see over here, it is called an acid catalyzed ring opening reaction, because we want to open this ring. You can see that we have a triangle over there. We want to open it, so we're gonna need a acid as a catalyst to open that. With water as well, it is needed to undergo reaction with this molecule to produce a diol, or we call it dialcohol or a glycol. Now, these are two steps that took place. From this step to here, we are talking about the two steps. No, the two steps, it's the oxidation and hydrolysis. Remember, hydrolysis, it is the addition of water. But you have to understand that at some point we added hydrogen atom onto there, which is more or less of a reduction. And then the whole combination of these two-step reaction, it is called hydroxylation, because we did a oxidation and hydrolysis. And then reaction number B, it is still under this reaction. Same applies when we take our epoxide, right? So, but here we are talking about a cyclic epoxide, meaning I'll take this from reaction number A. So this is supposed to be actually A1, not this. This is supposed to be A1 over here. So this is B1, this is A1. So, okay, we start from here to form an epoxide, which is a cyclic ether. This cyclic ether, under acidic condition with water, will form a diol. The stereochemistry, when it comes to these products, it is very important. We can see that from B1, our hydroxyl groups are attached in a trans formation. And then here, trans, it is also highly recommended. So what we see here is this, meaning our OH is supposed to be in different planes. So for A1, our cyclic ether under acidic condition, okay, this is the resonance that will take place as a mechanism between this and our H3O plus ions that are going to be added onto our ether. So we're going to form this at the end of the day. So now this is what is happening. What matters is you need to understand that when you add H3O plus onto this molecule, your OH that are going to be formed is supposed to face in different direction as a stereochemistry to indicate that the product that is going to be formed during this chemical reaction will be a trans. And I hope that was clear. So that's it about the epoxide. Remember, epoxide, it is oxidation reaction because we want to add an oxygen, right? So now since epoxidation, let me just write E to not waste time. Epoxidation. Remember, we spoke about two reactions, which is A and B. A, we talked about a cyclic ring. B, we just talked about an open chain. Now on a cyclic ring, we managed to form a cyclic ether. And then here we managed to form a cyclic ether. And then here we managed to form just an ether. So this ether to be formed, this cyclic ether to be formed, we need M, P, B, M, C, P, B, A. Same applies to here. We need M, C, P, B, A. Remember, M, C, P, B, A. It will help us to add an oxygen onto these molecules. So remember, we have the cyclopentene, which is alkene, and then here we have alkene again, but now in a chain. We're using this to form the product, and I hope that was clear. And then remember, the ending product of this reaction, say we have a cyclic ether, we can further take that cyclic ether, hydrolysis to add water under acidic condition, which is H3O plus ion, to form a diol. And this diol that's going to result, trans molecule is highly recommended based on the stereochemistry. And I hope that was clear. Oh, same applies to this one ether that is going to be formed. We're going to open that ring of ether. And then remember, hydrolysis under acidic conditions. And therefore, what are you going to form? We're still going to form a diol molecules. Again, stereochemistry does play a role in these reactions. Now, without wasting time, let us move to oxidation. Epoxidation and oxidation is addition of oxidation of oxygen. But here we can see that when we add the oxygen, we're going to form different products. It depends on alkene we are talking about, and it depends on the reagent that is being used for these chemical reactions. So under oxidation, we're going to talk about 3 reactions. We're going to talk about A, B, and C, 3 reactions. So now, A, let's have a look at the differences between these 3 reactions. This is the first reaction, the second reaction, and the third reaction. The first reaction, it is an alkene. We know here we also have an alkene. We can see that also here we have an alkene. But let's compare A and B. A and B. Alkenes are not the same, it is true. But now, what's the major difference that we want to focus on to? Here, it's true, both are rings, but you can see that this carbon atom and this carbon atom, they have hydrogens over there. This carbon atom and this carbon atom, they do not have hydrogens at all. That's very important. Okay, so here we have carbon attached here, we have carbon to these 2 consecutive carbon atoms. But between these 2 consecutive atoms, we have hydrogens and hydrogens. Okay, sharp, we still have carbons and so forth. Now, when you want to oxidate this alkene, it must be oxidated under the basic conditions. So that means our potassium permanganate, which is our reagent, we're going to dissolve it in a solution of sodium hydroxide, which is a basic solution. Therefore, this potassium permanganate will give the oxygen into this alkene. This is not a substitution, rather, but it is an addition. We still have the water in a solution, so you will understand. But remember, we are not focusing on the mechanisms why we have OH here, why we have OH over there. So the addition of oxygen onto this molecule will break this double bond, and then oxygens followed by H, whatever the whole process, the hydroxide will be attached to these ends of these carbon atoms. And you have to pay attention to this fact that the stereochemistry, again, it does play a role. So this is a cis molecule instead of a trans. It is true, when we spoke about the oxidation, we spoke about the trans. Be careful of that. And here, it is a diol molecule. Same applies here, it is a diol molecule. But you have to understand, this diol molecule resulted by oxidation, and this diol molecule resulted by epoxidation because we took a cyclic ether to form a diol. Here we took alkene to form a diol. So that means diols can be formed, so far, can be formed in two different ways. By reacting an ether, you form a diol. By reacting an alkene, you form a diol. Like I said, from here to here, we need two steps. And the name of the whole reaction is called hydroxylation. This is two steps. But from here to here, it's a one step. Only if we use potassium permanganate. Potassium permanganate, first, it forms a diol. But when we use peroxy acid, it is not going to be an accelerated reaction to form a diol. You're going to have to form an epoxide. That epoxide will further react to form a diol. Be careful of that, okay? Be careful of that. And then this is under the basic conditions. Now, number B, we're still adding our potassium permanganate to add the oxygens, but again, this reaction, it is called hydroxylation, which is what we did over here, hydroxylation. Okay, so here we're still adding our potassium permanganate to these carbon atoms, but now this is under acidic conditions. Okay, be careful. Here we said it is basic conditions, and then here we say it is acidic conditions. Immediately when you see an acid, let's say you forgot that there's supposed to be hydrogen atoms here. There are no hydrogen atoms, and then you forget the product that is going to be formed. Just look at your solution, whether the solution it is acidic or basic. Now here, our solution, it is acidic. How do we see this acidic? By H3O plus ions. We know this indication of these ions. Concentration of this, it shows that the solution, it is acidic. So that means in this acidic reaction, what are we going to do? Our potassium permanganate will help by adding the oxygen atoms into this alkene. So here, this type of reaction, it is called cleavage. So that means we're gonna have to break these carbon atoms, because we cannot add the oxygen, meanwhile we do not have hydrogen atoms. So in order for us to add oxygen, therefore the breaking is supposed to take place. We're supposed to cleave this alkene molecule to form two different organic compound. So here we know that after breaking this bond, the oxygen will be added on this part of this molecule of an alkene, and then the remaining oxygen will be added to this part of the cleavage of this molecule of an alkene, and therefore this is a cleavage. And then here we're no longer forming the diol like there. Here we're forming two ketones. And so I'm saying to you, addition of oxygen, it can form different reactions. It depends on what type of alkene has been used and what conditions has been applied onto a chemical reaction. So here is a cleavage, we form two ketones. The third one, I'll come back here. The third one, it is called the hydroboration, but this one is different. We're no longer using the potassium permanganate. Now, these are the reagents that are going to be used during this chemical reaction. It is still an alkene. We still need to break this double bond by adding oxygen. So here, we're not going to form a diol. Rather, we are going to form an alcohol specifically, like there. So here we can see that addition of an alkene, these are the reagents that are needed. I mean, like it's hydroboration. So the thing is, boron will be added, blah, blah, blah. Problem is this, it has a mechanism. But the simplest way to remember this is that, remember, under hydroboration, these are the reagents that we need. BH3, borane, THF, we need this H2O2 and then OH minus ions, and therefore this will be, you can see that it's a reaction that takes place in 2 steps. So but here from there to there, we just going to have to add we're just gonna have to break this double bond over there and add OH and H in this case, because we can see that this carbon doesn't have hydrogen at all. This carbon, it has carbon, it has carbon, it has 2 carbons. Now it is bonded 4 times with carbons, doesn't have a hydrogen. But the moment when you break this double bond, therefore hydrogen will be introduced. And therefore, again, stereochemistry, it is very important. We can see that the addition of these 2 elements that are new on this molecule, they're in the same plane. They're in the same plane. So stereochemistry is also important. So, but now you have to understand that regioselectivity under this reaction, OH group bonds to the last substituted carbon. This carbon, it is bulkier, and then this one is not bulky than like this one. This more is bulkier than this one. So that means our H will come to what is it? Our H will come to H group bond to the less substituted, and then H will be bonded to more substituted, and then OH will come over there. And then again, the stereochemistry is very important. So here we're talking about the sign addition, whereby H and OH, like I said, will have to face in the same direction, whereby the double bond existed. So basically, this is how we explain the oxidation. I hope that was clear. So now let us go back to here, which is number B. Number B, it is a subdivision of A. In this molecule, right? In this reaction, we spoke about the cleavage. So now let's say now, instead of us, here we had 2 hydrogen atoms, okay, sharp, it's fine. And then here we have no hydrogen atoms at all. Say maybe we have 1 hydrogen atom present between the 2 consecutive atoms that has double bond. So say we have this 1 hydrogen atom. We can see that we have only 1 hydrogen atom. Here it's carbon, carbon, carbon. We have only 1 hydrogen atom. So when you have a molecule that looks like this, you won't form 2 ketones. Rather, you will form a carboxylic acid. Okay, you'll form a carboxylic acid. We know that the functional group for carboxylic acid is COH. And then here we're going to have double bonded oxygen. So your oxygen is supposed to get there, because here we have H already. Oxygen will get there, and then oxygen will get there, and therefore another oxygen will get there. So between the two, where will double bond according to, but like I said, we don't have to discuss the mechanisms of this because we haven't learned them, okay? And we haven't gone through the mechanisms of this. Just know that when you have 1 hydrogen atom present, and therefore the reaction will further continue by forming a carboxylic acid. But remember, the reagent is still the same, still going to use potassium permanganate under acidic conditions. Be careful. That's why it's a subdivision of B, because you're still under acidic conditions. Okay. And therefore here again, if we have 2 hydrogen atoms rather. So now let's have a look at this molecule. So we have carbon here, we have carbon there, and then this is a double bond. So here we have hydrogen, and then here we also have hydrogen. So we have hydrogen and hydrogen. So how are we going to add oxygen in this case? We're going to add oxygen following basic mechanisms, and therefore the product that is going to result here will be carboxylic acid and carbon dioxide. So when you have 1 hydrogen, you form strictly carboxylic acid. When you have two hydrogen atoms, you're going to form carboxylic acid and carbon dioxide. So these are the synthesis of carboxylic acid. And so I'm saying to you, moving forward, when we get to carboxylic acid slide, it will be much more easier to remember that, we also learned this under the alkene. So you see, work will eventually decrease as we continue with the slides. Okay, so that's what is basically taking place. Now, let us focus on reaction number 7, which is halohydrin formation. So halohydrin formation reaction is when we add, look, this is halogen and this is hydroxide. So that means in this case, we're going to have to add water and Br2 to our alkene. So regioselectivity, it is also very important, which is more or less like a Markovnikov rule. So X, which is our halogen, supposed to be bonded to the less substituted carbon. And then OH from water molecule supposed to be on the more substituted carbon atom. So now let's have a look at this alkene. We have carbon and then we have carbon. This carbon, it is more substituted, meaning this carbon, it is bulkier. So say we want to add Br2 and water molecule into this molecule. So where will Br2 go? Br2 will go to less substituted carbon atom. We said this is the less substituted carbon atom. So that means Br, when breaking this double bond, remember this is addition reaction. When breaking this double bond, Br will have to come on this carbon atom. And therefore, where will OH from water molecule will go? OH will come to the more substituted carbon atom, or the bulkier substituted carbon atom, which is this carbon atom. Therefore, OH will come there. And these groups, alkyl groups, they are also there. And the stereochemistry is very important, faced in different directions. Now, A2, which is the halohydrin formation, we're still taking our. The difference is here now we have the ring, and this ring, this carbon atom, and this carbon atom, they have equal they have equal substituted groups, right? So this carbon atom and this carbon atom, there is no one that is bulkier than the other one. So how do we deal with situation like this? So we are used to regioselectivity, but here we're not going to do a regioselectivity. Rather, we're going to form two molecules. So this is a heterogeneous reaction. So that means in this case, Br2 will come there, and then Br will come there, and hydroxide will come there. So because you have two products, you can see that the first product, our Br, is on different plane to the second product. And then our OH, it is also on different plane to the second product. So here we form trans, and then there we can always supposed to also form a trans. So if Br is coming towards us, and then OH is supposed to go away from us. But if Br is away from us, so that means OH is supposed to come out of the screen towards us. Okay, so that's how this halohydrin formation works. So be careful on what you are adding. You are adding what on what molecule, on what alkene. So here regioselectivity is very important. Here two products are going to be formed with different directions of Br and OH. Now let's talk about the diols formation, which is reaction number 8. We're still adding. So here we're going to use osmonium tetraoxide, and we're also going to use the pyridine. Pyridine we have learned it. We'll also do it, I think, under aromatic chemistry. So this is an alkene molecule. We want to add the oxygen. So how are you going to add the oxygen? Remember, this is what we are going to do. We're going to use this reagent. This reaction, it is a two-step reaction. okay, which is 1, 2. So we're going to add we're going to have to break this double bond over here by adding oxygen on this carbon atom and this carbon atom. And therefore, this is how these oxygens were added. Obvious, OH will also be there. This is OH, okay? We're going to form a diol. Here's the thing. You need to be careful on how you forms your diols. It's true. This is an alkene. This is an diol. This is an alkene. This is a diol, right? This is where is it? This is an alkene, 2 steps, and this is a diol. So can you see that this diol and this diol and that diol that I've showed you are the same? But you need to be careful. You need to understand the reagents. So this diol, how did we manage to form it? We formed immediately when you see something like this, just know that there will be a further reaction whereby we're going to use HiO4 to remove. This is a reduction. This is oxidation. Remember, oxidation is addition of oxygen, but removal of hydrogen. And therefore, HiO4 for this reaction will remove these hydrogen atoms, and therefore we're going to have a molecule that looks like this. So my concern is you need to know that if I have an alkene to a diol, what did I use over here? If I used ammonium tetraoxide, pyridine, and number 2 NaHSO4. So now I know that I'm going to form a vicinal diol sharp. Fine. This vicinal diol can further go reaction with HiO4 to form this compound over here by removing the hydrogen atoms from the diol. Another way, when you have the alkene to form a diol, it's when I have what? Be careful of that. Now, to form this diol over here, it's when I have potassium permanganate, okay? So when I have a potassium KNMNO4, when I have potassium permanganate to form a diol, it is under what condition? Acidic or basic condition? It is under basic condition to form a diol. Okay, so we are revising now. Okay, this is under the basic conditions. We are taking notes. This is under basic conditions so that we don't confuse ourselves. Can you see that? All right, so here's whereby we're gonna use OSO4, pyridine. This, I don't want to waste time. This is the same thing that we're gonna use to form a diol. So that means this diol that's going to be formed over here can undergo further this reaction. You see, so moving from here to here, as long as you have a diol, just know how to treat your diol to form this product over here. But you have to be careful. This diol which is formed over here, it is a cis diol. You can see that these OH are facing in the same plane. So for you to form this, your OH is supposed to face in the same plane. Now let's go back to this reaction and see what is happening there. Where is it? Here it is. This is cis. So that means this reaction can go further by using HiO4 to form to remove these hydrogen atoms so that we can have O double bond over there, which is this molecule over there. See, now we are learning. Another way, alkene, where is it? Another one, it's this one. You see, so but here it's an alkene. Here we need 2 steps. Now we're doing synthesis. Here we need 2 steps. From an alkene, we're gonna form what? Ether. And then from ether, we're gonna form what? A diol. Sorry, a diol. And from a diol, we're gonna form what? We can form this molecule over here by removing the what? The hydrogens. Okay. But it's very important again on the stereochemistry. If we form cis diol over here, we can perform this HiO4 to form this molecule over here. So from an alkene here to ether, what did we use? Peroxy acid, right? We use peroxy acid. So alkene peroxyacid, it forms ether. And in ether to diol, we need acidic condition. If I remember, we need H3O plus ions. And therefore, from there, we form a diol. So the diol is cis. When the diol is cis, we're going to take HiO4 to form this molecule over there. Okay, so we're just revising not to confuse ourselves. All right. Now we move to number 9. Here we have polymerization reaction of alkene, polymerizations, formation of plastics, and so forth. So here we have an alkene, a vicinal alkene, okay? This is a vicinal alkene. There's chlorine over there. So that means you're going to have to break this double bond. So here we're going to use the peroxide acid. This is carboxylic acid. We're going to have to use peroxide acid and heat to break this double bond so that we can form a monomer that looks like this. See, this. And then here we're going to have Cl, H. This is a monomer, okay? After breaking this double bond, you're going to have something that looks like this. And therefore, this is the monomer that I'm talking about. Here. Okay, here. And therefore, these monomers will attach to form a long chain. Don't know how many number, maybe 2, 4, 5, 6, a long chain. And therefore, this is the polymerization of alkene, the reactions of alkene to form a plastics, PVC, okay? Polyvinyl chloride is called PVC. The last one, formation of carbene. The formation of carbene, again, we have an alkene. Now, this is a molecule that we call carbene. So how was this molecule formed? We use CHCl3 and potassium hydroxide. So that means CHCl3, it is going to dissolve in a strong base. So this is the basic solution. So this basic solution, there will be breaking of double bond between these two consecutive carbon atoms. And therefore, ClCl3 with some mechanisms will be attached. This carbon will come over here with Cl3s, right? Will come over here, this carbon atom. And therefore, this single bond will, like I said, double bond will break, and then we're going to have single bond. This is where single bond is actually located. But the rearrangement of this is a little bit different. Like I said, we don't do mechanism of this. So I saw its mechanism, but again, we do not do the mechanism of this. So the formation of carbene is going to form a molecule that looks like this. So the most reagent that we need is CHCl3 and potassium hydroxide as our base. Therefore, this will be the end of the revision lesson.